So to summarize this problem, with tightly coupled systems, you get amazing latency, but as your data volume grows, your cost to serve starts increasing a lot. And now we're not looking so great on the cost aspect of our triangle. Then coming to the other category of databases, which is like your data warehouses, data lakes, lake houses. So these went with the decoupled architecture from the beginning. And that was great because this is kind of the cheapest way you'll ever store data. So compared to our previous option, this is at least 5 times cheaper. And the great thing about this is that it's like shared across instances, and so your compute and storage can truly scale independent of each other. But on the flip side, if you look at the first 2 rows of this table, what used to be POSIX APIs that just took microseconds, milliseconds, is now network calls that's going to take 1,000 or 10,000 times longer. So with decoupled systems, we ended up trading off a lot of latency in order to save cost. And now we don't look so good on the performance aspect of our considerations anymore. Now what data teams end up doing is they will have both systems. They'll have a real-time system to keep the real-time data, set an aggressive retention, migrate the data off to the historical system. But with this, you're doing everything twice. You have 2 systems, you're maintaining 2 systems. Often you're like rewriting the logic of getting the data into both systems. And now we're not looking so great on the flexibility aspect of our considerations. So what we need is like a true best of both worlds, where we get the speed of a tightly coupled real-time analytics database, cost of a decoupled system that uses a cloud object store, and possibly have the flexibility of just using a single system to do all this and configure it in many ways. So this was our motivation behind building tiered storage in Apache Pinot. With tiered storage, now we are no longer strictly tightly coupled. We don't have to keep data always in disks or SSDs. We have multiple tiers, and one of those tiers can be a cloud object store. And then you have full control in how you want to, which data you want to keep in which tier. So one popular way to do this is by data age. So customers would typically set that, hey, before 30 days, I want it to be in the local storage. Beyond that, ship it to the object store. And then you can continue querying this table just like any other table transparently. It doesn't matter where the data is. And you can still operate Pinot in fully tightly coupled mode if you want, fully decoupled mode if that's what you want, or go for like a hybrid approach where some part of your cluster is doing a local mode, some part is doing remote mode. You can keep switching between these and so on. It's like fully flexible and configurable. So to just summarize that motivation with what we've built, we now have flexibility of using a single system for historical as well as real-time data without worrying too much about the cost. We did not talk yet about the performance aspect, right? So now that we've changed our architecture to have decoupled storage, are we going to go and start performing like those traditionally decoupled systems? So over the next few slides, that's what we're going to dig deep into, of how exactly we approached the performance aspect of this design. So in order to make Pinot work with a cloud object store, what we did was we enhanced the query engine to just be agnostic to the segment location. So behind the scenes, we built like our own data buffers, which could read from local, or if configured, they could read from an object store. But making it work was just part of the story. So Pinot is a system built for low latency. People come to us because of the speed that they get. So keeping that speed was very important to us. But as we can see from this table, we've now gone from something that used to give us microseconds, milliseconds, to something that's extremely expensive. Making it work was just part of the story. Now we've fundamentally gone to a different access method. And so how do we make it still be really fast? So we had figured out the make it work. Now we're on to let's make it fast. So we were thinking of this in terms of two key questions. One was, what data should we read? And then the other was, when should we read this data? So in what data to read? We store data as segments. Do we read the whole segment from the object store? Do we read a portion of it? How do we decide what portion we should read, and so on? And then when to read the data? Do we read it just in time like we used to when we were in local mode? Do we do some caching? Do we do some prefetching? Like all these sorts of questions. So the first thing that will come to anyone's mind when you talk about tiered storage is that, hey, this is easy, just do lazy loading, right? So lazy loading is a popular technique used by many other systems to offer tiered storage. In lazy loading, all your data, you'll just push it to a cloud object store. And then when the query comes in, it's first going to check if the data is available in the local disk, which you have to attach. And if it's there, well and good. If not, it'll have to download the segments that it needs from the cloud object store. Which means your first query is always going to be slow because it has to download a lot of data. But the hope is that your second query is able to reuse some of this data, and so it's going to be really fast. So here, what to read is like all of the data segments, when to read is during the query execution. But one thing about OLAP workloads in particular is that you will rarely have data that you are able to reuse query after query. In OLAP, you're going to have like arbitrary slice and dice and point lookups on different user attributes. So more often than not, what you've downloaded will not be useful for your next query. And then this instance storage is limited, so you'll have to constantly keep removing the data to make space for the new data, which is going to cause a lot of download and churn. And also, you're kind of fetching the whole data segments as they are, and this is going to be really wasteful in OLAP because typically you'll be querying like a column here and there, and you're rarely going to ever need like the whole, like all of your columns in your data segment. And there's always going to be some query that has to download all of the data, right? So in OLAP workloads, in real-time analytics, having a consistent, predictable P99 latency is very important. So because of that, this approach was a strict no-go for us. So we decided that instead of focusing on things like caching or lazy loading, how about we focus on like the worst case when data has to be read from the object store, and then what do we do? So to look for some clues, we started taking a look deeper into our Pinot segment format. So like I mentioned earlier, Pinot is a columnar store. So the Pinot segment file this is kind of like an illustration of how it looks. You'll have, let's say you had columns, browser, region, country, impressions, cost, timestamp. So all of these are going to be stacked one after the other in a columnar fashion. And even within each column, we have multiple data structures, like at the minimum, we have a dictionary and a forward index. On top of that, sometimes we have more indexes, like inverted index, range index. So you'll find all of these packed one after the other in this columnar file. And now what this allowed us to do is, instead of whole segments, we were able to do a columnar fetch. So let's take an example. If you get a query like, where you have filter on region and you're projecting the impressions, doing an aggregation on it. So in this query itself, you know that, hey, all you're ever going to need is region and impressions. So that's all we'll fetch. And then even beyond that, we know from our query plan that region is being used in the filter phase. So we maybe only need the dictionary and inverted index. So even everything else for region, we'll just not fetch it at all. We maintain a lot of mapping of where exactly to find what, so that we can just go and selectively fetch exactly what we need from the object store. And this seemed like a great start for us, so we went with this. The next question was, when should we fetch the data now that we know what we want to fetch? So earlier we looked at the Pinot, how the Pinot query flows from broker to the servers. Now let's take a look at what happens once the query reaches inside the server. The first thing is that we'll go through a planning phase where the server will look through all the segments that it has and decide which are the exact ones that it needs to process. And all those selected segments will be processed by the server in parallel by multiple threads. And if there are more segments than there are number of threads to execute them, then the threads will start executing them sequentially as well. So one simple idea here was that just before we start the segment execution, you fetch the columns that you want from S3, and then at the end of it, you release them. But when we put this to practice, this turned out to be not such a great idea. And that's because, again, let's take an example. Say you have 40 segments, you have the parallelism that you have at your disposal is like 8 threads. The round trip time for S3 generally is on an average like 200 milliseconds. So what's going to happen? You're going to execute these 40 segments in 5 batches, 8 at a time. And before every batch starts, all of those segments are going to wait to do a fetch from S3. And then when the next batch starts, again, they're going to spend 200 milliseconds to do a fetch from S3. This is going to quickly add up, especially when you take it to hundreds of thousands of segment scale and terabytes data. So this was definitely not something that we could afford in a low latency OLAP store. One key observation that we had here was that when data was being fetched from the object store, the execution threads were just waiting and the CPU was just idling. So could we somehow decouple the fetch and the execute, and then probably that would give us, take us some further along? So that's exactly what we did. In the planning phase itself, we know exactly what columns from which segments we are going to need. So there itself, we began, we issue a whole bunch of prefetch of all those columns. And now in the execution phase, the segments just wait for those prefetch to complete and then begin execution. So let's take a look at what happens when we compare the same thing with our new design. So before all these segments even got into the execution phase, the prefetch had been kicked off. So maybe the first batch of segments still has to wait 200 milliseconds to get the data available. But for any batch after that, the prefetch would have already completed, and so your total overhead is just going to be one round trip time of 200 milliseconds. So we put these two strategies to a test. So far we had in what to read was selective columnar fetch. In when to read, we had prefetch during planning, pipeline, the fetch and execution. And we ran this with several OLAP queries that had aggregations, group bys, filters. And then we also compared this with a traditionally decoupled system, Presto. And we saw that Pinot was able to be 5 to 20 times faster than Presto. So why is that? Even though we fundamentally changed the architecture to be decoupled, how are we still so fast? There's several optimizations in Pinot at every step of the query execution, which we are able to use even when the data is on remote storage. So bringing back the relevant components of the Pinot architecture again, let's say we have one broker, 3 servers, 12 segments, and each server has 4 segments, and we need to process all of these in our query. What the broker does is, when it gets a query, it has to figure out the smallest subset of servers that it needs to fan out to. And we have broker-level pruning techniques here, where we can create partition groups or replica groups, so we can just chop off server groups, whole server groups that we don't even need to go to. Same story at the server. The server has to figure out the smallest subset of segments that it needs to fan out to. And then we have very smart pruning techniques that allow us to just chop off segments that we just don't even need to touch. And this becomes super important when your access to a segment involves a round trip to an object store. And then we have filter optimizations, aggregation optimizations, like indexes that help us just reduce the amount of work done to get the exact matching documents that we need from each server, from each segment. Now let's dig a little deeper into the pruning techniques at the server and also the filter optimizations and see how we made them work even when we moved to remote store. So for pruning techniques at the segment level, we do have like the classic techniques of the min-max values and partition info that we store in each segment metadata. And these are by default computed and just kept in memory in all of the compute nodes. And that kind of lets us very quickly just read that and decide, hey, we don't even need to get to these segments on the remote store. An even more efficient technique is the Bloom filters, which will very quickly tell you that, hey, this segment is not going to have your data at all. But now Bloom filters are modeled as an index, which are now in S3 in each segment. But the thing about Bloom filters is that this is a very tiny data structure, and it's just like a fraction of the storage cost of the whole column. So to handle these kind of structures, we added one advanced way of how we can split the data across S3 and local. And where now we can be super granular, and we can say, hey, not just by age, but within that, I want this specific column to be always local, everything else on S3, or I want this specific index to be always local and everything else on S3. So typically with Bloom filters, what we then now recommend is just pin those on your disks and then keep all the bulk of the data on S3. And now this works great because lightweight structure, you just quickly read it, and then you're saving a lot of accesses that would have otherwise gone to S3. And you can do this for any column, any index, anything that you know that, okay, I'm going to be querying this very frequently, and you can apply this technique. Coming to some of the filter optimizations, we have a very wide range of indexes, and we're able to use all of these even if the data is on the remote store. So starting with classic techniques like inverted index, where you'll have a value and then bitmap for each value that quickly gives you matching documents, or a sorted index where you rearrange the data of your column so you can just quickly identify which value is where in your file. Or range index, similar to inverted index. This is great for range queries, like timestamp filtering or filtering on numeric values. So instead of value to matching documents, now we have range of values to matching documents. Other advanced techniques like JSON index, if you have complex JSON payloads, you don't have to spend time kind of flattening it out or expect your application to do some post-JSON extraction. We are able to just index every field in that JSON and let you query it extremely fast. Text indexes, if you want to do log analytics or free text search, these work with RTR storage as well. And then geospatial indexes, if you have location data, coordinates, and then you want to fire queries like show me the orders near me or show me the riders near me and so on. So all these techniques we are able to use even when the data is on tier, and that's why these are some of the reasons why even though we now fundamentally changed our architecture, we're still pretty fast compared to the traditionally decoupled systems. But if you look at the rightmost column, that's how Pinot in tightly coupled mode performs, and that's kind of our true baseline. So people have come to Pinot for that speed, and we wanted to kind of chase as much as possible that we get the speed as close to that. So this kind of told us that the techniques that we had so far are not enough to hide all the latency coming from S3. So we decided that, hey, we'll stress test this and try to find more learnings that will help us make the next design choices. So we kind of put 10 terabytes on a single node that had 1.25 gigabytes network bandwidth available. And then we ran a lot of different queries with different levels of selectivity. One of the key learnings that we had was that we are saturating the network pretty easily. And that's because even though we're doing columnar fetch, or we're doing pinning, or we're pruning segments out, because we're reading the whole column, we still are fetching a lot of wasteful data. And especially in OLAP, you will have a lot of highly selective filters. So reading the whole column is going to be pretty wasteful. And once the network is saturated, you are just at the mercy of what that instance can do, which is the 1.25 gigabytes per second. And then the other learning we had was that when network was not saturated, we had a lot more room to just do a lot of things in parallel and then reduce the sequential trips that we're doing to S3. So takeaways were read even lesser data, increase the parallelism. So to read even lesser data, we were like, how can we go beyond columnar fetches? So we decided that we will try to see if we can read exactly the block of data that we need from our column. Bringing back that same example from earlier, when we have an inverted index like this is pretty close to how it would have been represented in the real index file. So here we know directly that, hey, we don't need to read the whole index file. We have enough metadata to know exactly which block to fetch so that we will get the information for the filter that we're interested in. And beyond that, once we have read this index and we know the matching docs, maybe we just need to read these rows up there, these rows up here, which means we only need to read a few blocks from that whole impressions forward index. So that's exactly what we did. We changed our strategy from whole columnar fetches to reading precisely just the blocks that we need from those columns. And then we took this strategy for a spin. And if you look at the left section and the right section, when we went from columnar to block fetches, we saw a dramatic reduction in the amount of data that we're reading. And because of that, directly we saw our latencies also go down quite a lot. One index that we didn't talk about earlier in the indexing was the StarTree index. So this is like a very powerful technique that's a filter as well as aggregation optimization. So in StarTree index, it lets you kind of build pre-aggregations of your dimensions, and you get to choose exactly which dimensions, how many values to pre-aggregate, and so on. So let's take an example. If you had this data that had dimensions like name, environment ID, type, and more, a metric column called value, a timestamp column, and then you decide that, hey, I only want to create materializations for name and environment ID. I only care about the aggregation sum of value. And one very important thing here is the max leaf records. So basically this lets you choose that once I only am left with these many records in my materializations, I don't want to do any further pre-aggregations. So in this case, the StarTree that you will end up with will look like this. You'll have the name on the first level, you'll have environment ID on the second level, and then you'll store aggregations at each node. And if you look at some of those nodes, we just decided that we'll do no more pre-aggregations here because we have crossed our max leaf records threshold. So because of these fine tunings, StarTree lets you kind of choose your overhead between pre-aggregating everything and doing everything on the fly. And pre-aggregating everything is bad for storage, doing everything on the fly is bad for latency. So StarTree lets you choose your balance between these two options. And now if you get a query like this that has filters on name and environment ID or any one of them, it will just be one quick lookup in the tree to get to the right answer. Now, how did we make this work on tiered storage? You can imagine that this is a pretty large structure that involves a tree. Traversing through a tree is not like a remote-friendly reading pattern. Plus, like the whole aggregations that we're storing, you can't really like just pin the data or try to just read all of it directly during the query. So this is kind of where all our techniques came together. We were able to extract just the tree portion from the whole StarTree index, which again, pretty lightweight structure, which we were able to pin locally. And then once we traversed the tree locally and knew exactly where to look, we just did a few lightweight block reads on the remote object store. And once we made StarTree work on tiered storage, again, we took some really expensive queries that were scanning a lot of data, and with StarTree, we again saw very dramatic reduction in the amount of time that they took. Now, bringing this table back, So earlier I did show that, hey, we reduced the data that we read a lot by going to block reads. But if you look at the latency column, that did not really translate to a linear reduction in the latency. And why is that? So when early on in the learnings, I mentioned that when we're not saturating the network, we do have a lot more room to do parallelism and just speed up the fetches. This is kind of demonstrating that. So one technique that we explored to get more parallelism out of our query execution is a simple concept when we kind of know that, hey, these are the blocks that we need to fetch after we've applied the filter. These blocks in the post-filter phase can just be fetched in parallel. But now if you caught on to it that, hey, that means you're waiting until you apply the filter to start fetching this. So what happened to all the prefetching and the pipelining of the fetch and execution? So for that, we built sparse indexes. And sparse indexes kind of let us identify in the planning phase itself that, hey, these are the blocks that you might need once you get into your post-filter phase. So there itself, we start executing all these, fetching all these blocks in parallel. So by the time your filter is applied and you get to the post-filter phase, they're just waiting for you, ready to be operated on. So these are some of all our techniques that we applied in our tiered storage journey. So just to quickly summarize, we talked about the types of analytics databases, where Apache Pinot fits in that, what makes Apache Pinot really fast, the pruning techniques, the optimizations and filtering and aggregations. We talked about why we needed tiered storage. And then we went deep into how we implemented this. No lazy loading at all. In what to read, we came to columnar fetch, selective columnar fetch, doing block reads, sometimes reading nothing at all by doing index and metadata pinning. And then in when to read, we came to techniques like pipelining the fetch and execution, prefetching as much as we could, and then parallelizing the blocks that we need as much as we could. And we also shared some of the results that we got in the process of building this out. And then some future extensions that we are working on right now is to have even more flexibility in the ways that you can move data from local to remote. Like imagine if you could just say, hey, identify what are the hot segments and just keep those locally, move everything else to tier, or just as my data size just starts growing really large, start moving it automatically to tier. So practically never worry about running out of disk space. Other things we're doing is, now that we're fetching like tiny blocks, could we start somehow keeping them around if more queries are going to use them so that we can benefit from even lesser fetches across queries. Yeah, these are some of the things that we are working on in our continued journey towards tiered storage at extremely low latency. Thank you.